So this is a really common Calc 2 problem where you want to know how much work it takes to lift a bucket that's leaking. Now, sometimes you're going to get a little bit of a break and you can ignore the rope, but we're going to go ahead and do one where the rope has, some consequences and our bucket is leaking. It's going to be full of sand. It's going to be full of water. Doesn't really matter what it's full of, right? But it's going to be leaking at a certain rate. So when we want to figure out this work, a couple of things we're going to remember. First off, I've got a picture kind of drawn here for the setup. So our rope density, right? So the row of the rope is going to be 0.3 kilograms per meter. Okay. The height of the building, so we have to lift this whole thing 20 meters. The original mass of the bucket, right, when it's full at the bottom, is 25 kilograms, and then it's going to be leaking at 0.1 kilograms per meter, right, as we lift it up. So remember, work equals, right, force times the distance that it's acting over. And the force for us is going to be mass times gravity, right? So this is what we're going to have to kind of think about. And I'm going to treat them both separately. So we're going to find the work to deal with the rope, and then we'll find the work for the bucket. Okay, I'm going to find those two independently and add them together. Okay, so let's do the rope first. So for the rope, actually, let's look at the picture here. If we imagine this rope here, and right, we can set up our axes any way we want. So even though, right, gravity is coming down, and typically that would be a y, I'm going to go ahead and let this be the x-axis. And so, right, this distance here is going to be x, and this little chunk here is my little dx. Okay? So now let's go ahead and think about the rope here. So the work for the rope. I have force times distance. Force is, right, mass times gravity times the distance. And then the mass is the density times, so this, let's think about that, right? It was kilograms per meter. So I need a per linear amount here. And what it is that little chunk of dx. So the mass is actually rho dx. Okay, that's the mass in that little chunk that we're lifting up. G is our constant gravity. I'll go ahead and move that to the front. And then the distance, each of those different chunks of rope get to move, that's the dog, you're welcome, is x. Okay. And then what do those x's go from? From 0 to 20. I guess this is my 0 to 20. All right, so we would integrate that from 0 to 20. So rho g, integrating x dx, rho g x squared over 2, 0 to 20, rho g over 2 times, what is that, 400. Okay, so I'm going to keep this as the work for my rope, and we'll just put a little cloud around that and come back to it. Okay, so now let's think about the bucket. So for the bucket, right, again, it is force times distance. Oh yeah, why did I integrate that? Right, because it's all those little chunks that we're adding up. So we're going to do the same thing here with the bucket. So force times distance. The force is the mass times gravity still, times the distance. So for this one, right, the mass is going to be changing. So it starts at 25, but then it loses, right, 0.1 kilograms every meter. So the mass, right, is going to be 25 minus 0.1. So, right, x is going up. So I'm kind of changing my frame of reference now. Right now I'm kind of thinking of the bottom here as right, being my starting point. So minus 0.1 times x. Okay. So when it has this mass, okay, the amount that it's going to travel is just a little bit of dx, right? So, right, it has this amount of mass only for right? One itty bitty moment while it moves, that little bit of chunk of distance, dx. And then as soon as it moves, the mass changes because it loses a little bit more, right? It's not that it loses exactly like it goes up a meter and then it loses 1/10 of a kilogram. It's losing as it goes. So my distance is actually dx. And then we have our g. And so this is all happening. Again, my dx's, all those little things that move, go from 0 to 20. Okay, so g out in front. Oh, that's nice and easy. So 25x minus 0.1 x squared over 2, 0 to 20. So I've got g times 25 times 20 minus 0.1 times 20 squared over 2. So this would be the work for the bucket. Okay, so we can go ahead and put all of those values in and we'll add these together. So here we go. Our total work is the rope, which was rho, which was 0.3, times g, which is 9.8, divided by 2 times 400, plus for the bucket. So I'll have another 9.8. Sure, you could have factored that. I'm being totally lazy and I'm going to grab a calculator. I hope you will too. 25, that'll be what? 500 minus, going to be 400, 200. 200 times 0.1 will be 20. Okay, so the total work that we're going to have, and I'm not sure if my calculator screen, oh look, it's not too bad today. So 0.3 times 9.8 times 400 divided by 2. So that was our rope. I'm just going to do a little, just so we kind of know what they are. And then plus 9.8 times 480, 4704. So 5292, and work, when we're talking about kilograms and meters, is in joules.